Well, we're going to continue with Chapter 3, the end of Chapter 3, with a discussion of solutions and solution in chemical situations. Some basic terms that we need to discuss first, and I'd ask you to focus your attention over there to the right where you can see what is obviously a solution that we're going to make as we dissolve some salt that's in that spoon in some of the water which is in the glass. And we have terms that apply for these different things. First of all, the solvent is what's there in the greatest amount. And in this case, the water, obviously, is there in a much greater amount than the salt, and so the water is the solvent. The solute is what's there in the smaller amount. It's what is dissolved in the solvent. In this case, the sodium chloride is the solute, and that these two things together make up what's called the solution. So we've just made a sodium chloride or salt solution by dissolving the solute, which is salt, in the solvent. By the way, just a word that applies here, until things are properly mixed up, the word heterogeneous mixtures would be used because we can visibly see differences between the liquid solvent and the salt. But when we finish mixing this up and all of the solute has dissolved completely, why, we'd have a homogeneous mixture. So, the solute is always that which is there in the lesser amount, and it's dissolved in the solvent, which is there in the greater amount. Some terms that apply to different types of solutions. The unsaturated solution is the one in which you can still dissolve even more solute. The saturated solution is the one in which no more solute will dissolve in the solvent. As a youngster, I liked cold cereal, and on my Cheerios I would pour milk and then I would sprinkle sugar to make them sweeter. And much to my parents' annoyance, I would often sprinkle way too much sugar, and I like to tell people that I was looking for the most highly concentrated solution of sugar and milk that was humanly possible. What I was really after was a solution that was saturated with sugar. And how did I know it was saturated? Well, if you've got a saturated solution and no more solute is going to dissolve, why then, if you add more, where is it going to go? Where will that extra solute go? Why, it just sinks to the bottom, and in the case of my milk and sugar experiment as a youngster, it just sinks to the bottom and stays there, at which point you can scoop it out with your spoon and eat nothing but pure sugar. But I digress. You get the idea. Saturated solutions, no more solute, or sugar, will dissolve. You might think that that's the end of the road. It's not. There is another third type of solution. It's called a supersaturated solution, and it's not something that occurs really readily in nature. This is a solution in which more solute's been dissolved than really should dissolve. These solutions tend to be rather unstable, and when bumped or disturbed in some way, usually what happens is the dissolved solute that has been dissolved but ought not to be very quickly turns back into a solid and sinks to the bottom of the container where the solution is present. Now, in chemistry and in biology, it's frequently found that the solvent of interest is water. As a biological solvent, we are mostly made up of water with some other trace elements, and having water as a solvent is a very important thing to be aware of. Whenever water is the solvent, the term aqueous applies. It's derived from the Romance languages, agua, aqua. You may have some foreign language in your past experiences, but aqueous means that the solvent is water. It's common in chemical and biological systems. And in chemistry, we are going to be working with solutions, and we're going to need to be aware of subtle differences between solutions. But not only the identities of the solute and the solvent, but subtle differences in the concentrations of solutions. One of the ways in which the concentration of a solution can be determined is by way of the mass percent concentration, which compares the mass of the solute to the total mass of the solution by dividing the two and then multiplying them by 100 to make it a percent. This mass percent concentration system is used in the allied health fields, often, for example, in a drip IV, where the concentration of the saline solution would be written on the bag as a mass percent by a mass percent concentration value. To show you how this would work, let's just consider the following simple example, imagine that we have 4 Erlenmeyer flasks. And these 4 Erlenmeyer flasks are filled to the same level with solutions that are obviously different in concentration, assuming that the solute is the same in all of these cases. Now, one thing, just to level the playing field somewhat, is that in all cases, 200 grams of water were used to construct each of these 4 solutions. And so the amount of solvent in each case is the same, 200 grams. The differences arise, though, from the fact that we have different amounts of solute dissolved in each of these 4 amounts of water. The solute is copper 1 chloride, and if I light up the solute line here, you'll see that the one on the left had only 5 grams of copper chloride dissolved in it, whereas the one on the right had 100 grams of copper chloride dissolved in exactly the same amount of water, about 20 times more solute. And so it's pretty easy to see that the solution on the right is quite concentrated in comparison to the solution on the left. We do use words to describe these differences. For example, the words that would apply to the left-hand Erlenmeyer flask would be least concentrated. Another way of turning this around is to talk about how dilute it is, and it's the most dilute, meaning there is a great amount of solvent and only a small amount of solute. On the right-hand side, we have the other extreme. We've got the most concentrated solution, or if you prefer the term dilute, the least dilute solution. These words are used to qualitatively describe differences between solutions. Qualitatively, you may be able to see differences just in terms of how dark the solutions are, and you may be able to line them up and say, this one's more concentrated than that one. But that's not going to be good enough for us here in chemistry. We're going to need to determine the mass concentrations for each of these 4 different Erlenmeyer flasks and the solutions that are within them. To do that, to determine the mass percent concentration, what we'll do is we'll compare the amount of copper chloride to the total mass of the solution. Now, that seems straightforward, and it really is, as long as you pay attention to the details. We only had 5 grams of copper chloride in that first solution, but the details I'm referring to here are that the solution's total gram amount is not 200 grams of water. It's the combination of the water and the copper chloride that we have there for a total of 205 grams total. Now, if we do the division and go 5 divided by 205 times 100, we find that the concentration of this solution by mass percent is 2.44%. A small number suggesting that it's a very dilute solution. If we do these calculations for the remaining 3 solutions, here we've got 20 grams of the copper chloride solute. The total mass of the solution is now up to 220, the water plus the copper chloride. We do the division, multiply by 100, and the result is a 9.09%, 3 significant figures, solution that's clearly more concentrated, that is, a larger number, than what we had for Erlenmeyer flask number 1. For Erlenmeyer flask number 3, solution 3, we have 50 grams of copper chloride. The total mass of the solution is now up from 205 to 250, combining the 200 and the 50, and it's a 20% solution by mass. And lastly, the most concentrated solution of the bunch, we had 100 grams of copper chloride in a total of 300 grams of copper chloride and water solution times 100 gives us a 33.3% by mass solution. As we look at these numbers from left to right, indeed, we go from smaller to larger numbers, telling us that we are going from more dilute to more concentrated solutions from left to right. Although mass percents are found often in the allied health sciences, they're not used as often in chemistry. And the solution concentration system that we use in chemistry is based upon something called the molar concentration, or simply molarity. And molarity, it compares solute, as we did with mass percent, but it compares it not as grams of solute, but as moles of solute. And it doesn't compare to the total grams of solution, it compares to rather the liters of solution. And so we calculate molarity by going moles of solute divided by liters of solution. And there's no factor of 100 either. So if we go back to the original problem that we started working with, and instead do the calculations based upon molarity units, here's what we would do. The first change is that instead of 200 grams of water, knowing that the density of water is 1 gram per milliliter, what we really have is 200 milliliters of water. Now I've done something else here too. Not only is a 200 gram solution, a 200 gram Erlenmeyer flask of water the same as 200 milliliters, but 200 milliliters is the same as 0.200 liters. And our definition for molarity requires that we have the volume of the solution in liters. So there you have it. In all cases, we have 200 milliliters or 0.2 liters of water present. That's the first change. The second change is that when we look at the solute, we don't want grams of solute, we want moles of solute. Now, to convert grams to moles, you're going to have to go to your periodic table and determine the molar mass of copper chloride, CuCl. Look up copper, look up chloride, add the two molar masses together, and then divide that into the gram amounts that I provided you on the first slide. I'm going to save us all of that arithmetic, and instead I'll just show you how the gram amounts on the previous slide convert into moles using the molar mass of copper chloride. And here they are. The first 5 grams or so of copper chloride works out to be 0.0505 and so forth moles of copper chloride, and across the board increasing numbers of moles of copper chloride because after all we had greater and greater gram amounts of copper chloride. Now we've got things massaged into the right units. We've got moles of solute, that's copper chloride, and we've got liters of solution. Be aware that in many real examples, the volume of the water may be somewhat less than the volume of the solution. You might think that makes sense because after all we're dumping in more copper chloride, and shouldn't that take up some space, and shouldn't the volume of the solution be somewhat larger than the volume of the water? Well, that's true. But to a first approximation, as long as we don't make solutions that are too highly concentrated, we can assume that the volume of the water is close enough to the volume of the solution that we don't need to be aware of any volume increases, the result of adding copper chloride. So we'll assume that the 200 milliliters of water will be, in fact, the volume of the solution. Let's do the arithmetic and see how it works out. The molar concentration, that is, the molarity, is always the moles divided by the liters. And so I've just taken these two amounts and divided them to determine that, to three significant figures, the molar concentration for the first solution is 0.252 m, or 0.252 molar. Moving ahead to the second solution, and using the numbers appropriate for that, we find that the solution's concentration is 1.01 moles per liter. Now here I've substituted the words moles per liter for the letter m. They're interchangeable. M means moles per liter, and moles per liter means m, or molarity. Solution number 3, again using the moles appropriate for that, and the 0.200 liters of solution gives us 2.52 molar, and solution number 4 has an even higher concentration, approximately 5 molar in copper chloride. The highest concentration on the right, the lowest concentration on the left, in agreement with the words that we use, where the least concentration and most concentration go from left to right. There are some relationships that you should probably commit to memory. We'll be using molarity and its definition time and time again, and it's good to know how these definitions can be rearranged. Now, the first definition that we've just finished with is that for molarity, and molarity is always moles of solute divided by liters of solution. And if you're like me, that'll probably be good enough. I can rearrange this formula in any way that I like, depending upon the type of problem that I'm working. But if you're not comfortable with the arithmetic or the algebra, feel free to memorize the following two formulae. Here's a rearrangement where if you were given molarity and given liters, it's telling you to multiply the two together if what you want are the moles of solute. It's just a rearrangement of the first equation, but it gives you moles of solute if what you have given to you is molarity in liters. Of course, there are three variables, and therefore there has to be three ways of rearranging this equation, and here's the third. If what you are given are moles of solute and molarity, why then you can just divide these two and determine how many liters of solution there must be. Commit these to memory, be familiar with them, be comfortable with them, start practicing with them right away, work homework problems, because this is a definition we'll be using time and time again throughout the semester, and if you go on to take 1152, it's assumed that you're comfortable working with molarity units. One of the types of problems having to do with solutions that comes up often is that of dilution. Now, you have experience with dilution. If you're like me and you've ever drank orange juice or made orange juice up out of the freezer, you're familiar with the following recipe. You take 1 can of concentrated orange juice out of the freezer, or if you've thawed it, out of the refrigerator, and you dump that into a pitcher, and then you add to it 3 cans of water. Water would be the solvent. And you mix these two things together. What you've done is a dilution where you've diluted with water the original concentrated orange juice, and if you follow the instructions, what you get is something that tastes like orange juice and is neither too strong nor too dilute to be palatable. We're going to look at dilution a little bit more carefully than that. And to illustrate this, let's consider this example. It's the same idea as the orange juice example. Here we've got, though, an iron chloride solution, which is nothing you'd want to drink. Its known concentration is 1.56 molar, and we're adding to that some amount of pure water. This process, this procedure, is called dilution. Adding two things together of known concentration. It just so happens that in the case of the water, why, it has no concentration of iron chloride whatsoever. It's pure water. When we're finished with this and the contents of that first flask has been properly stirred, what we're left with is a more dilute concentration of iron chloride solution, and that pale green color is there to remind us that it isn't as concentrated, and the level is up a little bit because, of course, we've added water to it, and the volume of the two solutions is what we have now in this final figure. And the water flask is empty as we've added all of the water to the original green flask. We are going to work with this example, though, in more detail, and to demonstrate this, what we're going to need is some additional information. In addition to knowing the concentration of the original solution, we also have been provided information about its volume. And there are 95.6 milliliters of original iron chloride solution whose concentration is 1.56. We also know something about the water. In this case, a total of 53.3 milliliters of water were added to the original highly concentrated iron chloride solution. So now we have molarity and volume information, and what we hope to determine, illustrated by that question mark off to the right, is what is the final concentration of the dilute iron chloride solution. Now, keep in mind that there are ways of telling whether you've got the right answer or that you've got the wrong answer. We already know how what concentration means, and if we start with a 1.56 molar iron chloride solution, we had better wind up with a concentration, a value that is less than 1.56 molar. After all, we're adding water, we're creating a more dilute solution, and more dilute solutions mean lower concentrations. So the final answer had better be a number that is less than 1.56 molar. Let's take a look at how we would actually calculate that. The way to approach this is to recall a formula from the last slide, where if you have the concentration of a solution and you know how much volume it occupies, we can take these two numbers and multiply them together. Now, I've done this rather quickly for you here, but I'll call your attention to something that is quite important, and that is that to do the calculation, I need to take the molarity of the solution, which is plainly 1.56 molar, and I need to multiply it by the volume of the solution in liters, not in milliliters. And so the volume, 95.6 milliliters, had to be converted into 0.0956 liters before I could do the multiplication. So I've got the 0.0956 liters there. I multiply the two numbers together, and what I find is that in terms of the moles of iron chloride, I've got 0.149136 moles of iron chloride present in that green Erlenmeyer flask that you see there. Well, the next step of this problem, to continue it, is to understand how much iron chloride I had at the beginning. Now, the iron chloride was present only in the green flask. Adding water to the green flask did nothing to the iron chloride, and therefore the number of iron chloride species present at the beginning ought to be the same as the number of iron chlorides present when the problem is finished, when the dilution is done. So, the number of moles of iron chloride that I calculate initially in this case, seeing as how no iron chloride is being added, must be the same as the number of moles of iron chloride after the dilution is complete. Okay? So this number is carried forward into the second part of the problem because I was adding pure water. If I hadn't been adding pure water, if I had done something that would have increased the number of moles of iron chloride, well then it would be a completely different problem entirely. Okay, now that I know the moles of iron chloride, same as what I had to begin with, I need to think about the definition for molar concentration. And going back in my head to that definition, it's moles divided by what? By liters of solution. So I need to know how many liters of solution I'll have once the two solutions have been combined. Well, it won't be 95.6 and it won't be 53.3. The volume occupied by the solution when the dilution is complete will be the combination of the two volumes that were put together. After all, their volumes added together and gave me an end solution that was higher on the level mark of that Erlenmeyer flask. And so I'll look at the 95.6 and the 53.3, and I'll say the final solution would have a volume that combines these two amounts, or 148.9 milliliters, all totaled. Good. I now have the two pieces that I need to calculate a concentration: the number of moles of the solute, 0.149, and the volume of the solution when it was all over, and that is 148.9 milliliters, or 0.1489 liters. I'll have to be faithful to that liters definition again. Taking moles and dividing by liters, I take 0.149 divided by 0.1489 liters, and the solution's concentration comes out to be 1.00 molar iron chloride. Does this sound reasonable? It's always good to look back. Recognize that the original solution's concentration was 1.56 molar, higher than the dilute solution's concentration, 1.00 molar. If I've done my arithmetic right, this looks like the right answer. We frequently work with solutions in a more chemical context. Dilution calculations do pop up and are often used, especially by those of us who work in the back lab, when we need to dilute concentrated solutions to make them appropriate for you to use in the lab. But here's a different type of example. It involves solutions and stoichiometry. We've done reaction stoichiometry quite a bit throughout Chapter 3. Grams, grams to moles, mole ratios, moles to grams, and all of these sorts of things. But here we have a problem that again involves a balanced chemical equation, but instead of being given gram amounts of things, we're given information about reactants in terms of concentrations and volumes. Now, the pattern of the problem is very similar to those stoichiometry problems we've worked in the past, but the way the initial information is being provided is a little different, as it has more to do with concentration molarity definitions. So let's take a look at problem 3.10 and read through it. How many grams of sodium hydrogen phosphate are required to react with, and then in red, 38.74 milliliters of 0.275 molar sodium hydroxide? There it is, a volume amount and a concentration amount. And we know what to do with those things. We know that if we multiply them together and we're cautious and we get things into liters units, why, we're going to have moles of sodium hydroxide. That's in the spirit of everything we've done here so far today. Okay, they'd like to know how many grams of sodium hydrogen phosphate are going to be required. Let's see if we can't fit this information into the structure of the problem that we've already done in the past and that we're comfortable with. I like to place these pieces of information right where they belong, and the 38.74 milliliters and 0.275 molar, well, that belongs with the sodium hydroxide. What we'll do is we'll convert this information into moles of sodium hydroxide, at which point this problem becomes a lot like the problems we've worked in the past. Once I've got moles of sodium hydroxide, then the blue arrow tells me I'll be converting from moles of sodium hydroxide using a mole ratio of 1 to 2 into moles of sodium hydrogen phosphate, okay, using the mole ratio. And to finish off the problem, since they wanted me to calculate the number of grams of sodium hydrogen phosphate, I'll need to convert the moles into grams using the molar mass, which has already been provided for me, the 119.97701 grams per mole. That's the structure of the problem. Let's go ahead and fill in the details. Returning now to the information in red, the 38.74 mils and the 0.275 molar, I recall that moles is equal to molarity times liters. And taking the two numbers I've been given and substituting them, I find that moles is equal to 0.275 molar, and that don't forget, you've got to have those milliliters in the units of liters, and so that'll be a 3 decimal place change to the left, or 0.03874 liters. Take these two numbers, multiply them together, and I get this result, 0.0106535 moles of sodium hydroxide. And that number needs to be entered right there. So far, so good. This is beginning to look like a very familiar problem. The only difference was getting the initial number of moles of sodium hydroxide, which was actually quite painless. Now, if we want to finish off the problem, we'll have to apply that mole ratio that we get from the coefficients of the balanced chemical equation. So I'll begin with the moles of sodium hydroxide in red there. I'll multiply by the mole ratio in blue to convert into moles of sodium hydrogen phosphate. And if I stop there, I'll have divided the original moles of sodium hydroxide by 2. I get 0.0053265 moles of sodium hydroxide, and that goes right up there in its space next to mole amounts. Then to finish things off, I'll have to convert that into grams using the molar mass of sodium hydrogen phosphate. That's 119.97701. I'm getting a little loose with my dimensional analysis here. Hopefully you can follow that. The end result of this with 3 significant figures would be 0.639 grams of sodium hydrogen phosphate. By the way, the 3 significant figures, if you're wondering where 3 came from, all you have to do is look back in the problem, and of the given information, the 38.74 and the 0.275 molar, it's the 0.275 molar 3 significant figures that affects the significant figures throughout this problem. A chemical titration is another example of a solution stoichiometry type of problem. And in lab this semester, you're going to be doing a number of titrations having to do with acetic acid and vinegar and a number of different things. You'll get plenty of practice with these calculations in lab, but let's work through a titration example here for you just so that you see how these sorts of things work. Now, this is an acid-base titration. And a titration is performed when you have a burette, as you can see here, and the burette with its valve is used to add, in this case, small amounts of sodium hydroxide to the hydrochloric acid that you see in the little Erlenmeyer flask down below. As you add sodium hydroxide to hydrochloric acid in this way, you're going to observe eventually a persistent color change. The idea here is to obtain a color change that is as faint and carefully defined as possible, and at that point the indicator that's present changes color, it persists, it's a very faint color, and you can be assured that the number of moles of sodium hydroxide that you've added will be equal to the number of moles of HCl. This is the chemical equation that describes what's going on. It's balanced. We see that it's an acid-base neutralization reaction. The base is sodium hydroxide, and the acid is HCl. It's balanced, and what's formed as a product? Pure solvent, water, and an aqueous salt, sodium chloride. There we have the base and the acid identified, and it's what we would call an acid-base neutralization reaction. Now, if we go back to the sodium hydroxide and read off the bottle label, we would know its concentration. We would also obtain the volume of the sodium hydroxide by watching very carefully the burette and noting the initial and the final volume amounts. We'll go through that in just a moment. We'd also need to know something about the concentration of the hydrochloric acid or the volume of the hydrochloric acid. All four blanks, of these four blanks, three of them we must have values for, and the fourth can be treated as an unknown as we solve these kinds of problems. Let's say that we don't know what the concentration of the sodium hydroxide is. Let's say that we do know what the concentration of the hydrochloric acid is, that it's 0.485 molar. And also let's say that we know what the volume of the hydrochloric acid is. It's 5 milliliters. Okay? We know quite a bit about this problem, but what we don't know is how much sodium hydroxide has been added. To know this, we would actually do the experiment. The first thing that we would do is we would measure the initial volume. We would read that off the burette graduated scale. In lab, your lab instructor will say things about how best to read a burette. Let me comment here that a burette must be read, unlike a graduated cylinder, from top down. Many people would mistakenly read this burette and its initial volume reading to be 1.15 or something like that. And that's totally wrong. You've read it from the bottom up. Burettes have to be read from the top down. And reading from the top down, this would be correctly read to be something on the order of 0.85 milliliters. For the purposes of this discussion, we're going to call it 0.86 milliliters. Okay? And we can agree that that's fairly close to my original estimate and that it's plus or minus 1 in that last significant figure. So that's the initial volume. Now, we do the experiment and we open up the valve. We let small amounts of sodium hydroxide into the flask beneath and we stir constantly, making sure that the reactants are very thoroughly mixed. We observe a faint color change, and at that point we stop the titration and we recognize that the final volume is now down here past 4. In fact, it's past 4.5. To the best of my ability, it looks to be a final volume of approximately 4.55 milliliters. As you look back at the initial volume and the final volume from the burette, see that it's possible to get 2 decimal places. All burette readings must be made and must include 2 decimal places to be considered correct. If you think it's 4.50, that is exactly 4.5, and it's clearly not, you would have to include 4.5 and then the number 0 following. But this final volume is really 4.5 or something quite close to that, and so that's the value that we're going to use. We know the initial and final volumes now. What we'd like to know also is how much sodium hydroxide has actually been added. So we subtract these values, 4.55 minus 0.86, and the difference between them is 3.69 milliliters. That's the amount, or the volume, of sodium hydroxide that's been added during the titration experiment. Well, good. We've got a lot of information here. We know the concentration and volume of hydrochloric acid, and now we know the volume of sodium hydroxide. We've got 3 of 4 unknowns covered. What's left to us is work through the arithmetic and determine what is the concentration of sodium hydroxide. For this, I like to return to the balanced chemical equation to organize the information better. For the hydrochloric acid, we know that the concentration is 0.485 and the volume was 5.00 milliliters. And for the sodium hydroxide, we don't know yet. Let's just follow these numbers through. Since we've got for the red hydrochloric acid, we know its concentration and volume. We also then can multiply the volume and the concentration together, being sure to convert the milliliter amount into liter amounts. We can multiply these two numbers together and determine how many moles of HCl we have, and that's what I've done for you in this step outlined in red. 0.485 is the molarity times the volume in liters, 0.005, and that gives us 2.45 times 10 to the minus 3 moles of hydrochloric acid. And so there it is, belonging with hydrochloric acid as advertised. The second step of the problem would be then to use the mole ratio that we get from the balanced chemical equation to convert moles of hydrochloric acid into moles of sodium hydroxide. And because it's a 1-to-1 ratio, why, the arithmetic is very simple. We would have the same number of moles of sodium hydroxide as we had moles of hydrochloric acid. We can do this only because the mole ratio is 1-to-1. If it were 2-to-1 or something else, why, there'd be a calculation involved. Now, we're nearing the end of the titration part of the problem. We know the number of moles of sodium hydroxide, and we know the number of milliliters of sodium hydroxide. So we have mole amounts and volume amounts for sodium hydroxide. Given these two numbers, we really have the pieces of information we need to calculate molarity. And of course, as always, we'll have to convert that volume into liters before we do the calculation. So, if what we want is molarity, we'll have a division ahead of us. We'll take the moles, as I've illustrated for you in the lower right-hand corner, the moles of sodium hydroxide, and we'll divide by the liters of sodium hydroxide solution that we used, and that was 0.00369 liters. And the concentration of sodium hydroxide, well, that would be 0.65718157, a glorious number. And of course, we'll have to round that off a little bit. How many significant figures are we going to need? Well, we're only going to need 3. If you look way back at the numbers that we've used, the hydrochloric acid concentration was 3 significant figures. The volume amounts that we've used have all involved 3 significant figure volumes, and so 3 significant figures in the final answer, and the concentration of the sodium hydroxide would be correctly reported as 0.657 molar. Just to review with you, a couple of slides here at the end which I think would probably be better simply printed off. I'm not going to spend a lot of time talking about them, but it's a nice way of looking back at Chapter 3 to discuss how various things can be calculated. And this first slide has to do with the traditional mass mole stoichiometry type of problem where you're given masses, mass of A, mass of B, mass of C, mass of D, and so forth, and then you convert them into moles of A, moles of B, moles of C, moles of D, using molar masses. And then you use mole ratios, and I've given an example there in red to demonstrate how you could use the molar ratio of A to B or B to A as a 3-to-2 or 2-to-3 ratio, and then another one there to show you that you can do the same thing as you work from A to C in blue. Just a very simple structure, a fairly straightforward problem-solving procedure, but something that if you work at trying to solve problems like this consistently, you'll have a pattern, a framework within which you can solve these problems, and you'll feel comfortable when you see these problems coming at you in, say, an exam situation. Okay, that's the conventional gram to mole approach. But what we've added to the mix is the following slide. You probably didn't see too much of a change there. Most of the problem remained the same. But what does change is that if you're instead given volume and concentration quantities for either A, B, C, or D, what does change is that you multiply these two things together to give you the moles. And then from that point on, the problem becomes exactly the same as a gram-mole stoichiometry problem. So print these out and use them if you like as you develop your own problem-solving technique. But regardless of whether you're doing a gram to mole conversion type of stoichiometry problem or a solution stoichiometry problem, in principle it's always the same. You make the mole your goal. Once you get moles in place, why then you can solve the problem by using the mole ratio. But the only way that a chemical equation like this works is when you're working with moles.